Hello and welcome to this video on HVAC System Parts, one of the beginning level series of videos here at MEP-Precon.com. My name is Ken Dykman, and make sure to utilize the slider bar at the bottom to either rewind any concepts that might be new to you or fast forward anything that you already know about. And if you found this directly on YouTube, make sure to stop by our website to get the assessment and take the assessment at the end of this video to test your learning, make sure that you got all the concepts from this video. All right, well, let's dig into it here. The objective of this particular video is, again, high level, just understanding what HVAC systems are and why they're important. We're going to introduce some components and talk about how they operate and considerations that you might want to think about as a project manager from a technical standpoint. Okay, so what is the purpose of HVAC systems? I mean, think about it. What do they really do? Because architects don't really like us too much. We take up a lot of space in the ceiling plenum and maybe sometimes mechanical rooms and sometimes maybe ugly things on the outside. I don't know. I think they look nice, but sometimes architects may not like them. So what's the purpose of them? Well, they control comfort, don't they? And when we talk about comfort, mainly temperature and humidity. Environmental stability. So if you have some kind of a process going on, maybe a lab, or some type of hospital process, we want to make sure we have a stable environment for that. We're going to use that to manage the energy usage in a building too. So HVAC is good for, and the controls of HVAC is good to make sure that the energy bills stay as minimal as possible. Also to control fire and life safety. Now we use certain devices, which we'll talk about in a little bit here. It's not going to prevent the building from burning down, just like sprinkler systems. They're not necessarily designed to keep the building from burning down, but they'll give the occupants a few more minutes to get out of the building. And if that saves 1 or 2 lives, then it's worth it that way. So yeah, HVAC systems are probably pretty important, and that's why we coordinate with the architect, even though other people may object and think that some of our systems are noisy and loud and ugly, but they're pretty important to have within a building. So what do we mean by air conditioning? What does air conditioning actually mean? Any thoughts on that? Well, mostly cooling. When people think air conditioning, it's usually synonymous with cooling, but it could be heating. Heating is conditioning of the air, it's heating it up. Could also be humidifying it or dehumidifying it. We could add some humidity with steam is probably the most kind of logical way to think about how to add humidity to it, or we can wring the moisture out through a desiccant dehumidifier or by cooling it with a coil and removing it from a condensate standpoint that way. Could filter it. Filtering is a form of conditioning it as well, not just for particulates, but maybe even deodorizing too. And so deodorizing is a way of conditioning it. How do we deodorize air? Well, we use a filter called a carbon filter. Very similar to a carbon filter if you have an aquarium of fish. It does a really good job. The odors are essentially very small vapors in the air, vapor particles, and so carbon, it has an affinity to those types of vapors in the air, and so that's how it is able to remove odors from the air. Okay, let's get into some parts now. Let's talk about fans. Different kinds of fans here. There's axial fans. And these are the fans that you would typically see, like a box fan that you would buy from a big box store or a hardware store. You would put it inside of a doorway or something like that. And so that is, those are usually meant for high volume and not a lot of static pressure. When we talk about static pressure, that means the ability to push air down maybe a long duct run that has a lot of resistance against it. These would be popular inside of maybe garages where we're going to remove a lot of air, but not push against a lot of static pressure. We don't have a lot of distance to take that air before it gets to the outside. Then there's centrifugal fans, and these are better at static pressure. So the hallmark of a centrifugal fan or a centrifugal pump is that the air comes in and it goes out at 90 degrees from each other. What I mean by that is here's where the inlet of the air comes in at, and it spins around and it goes out. And there's some other great animations on YouTube that you can search about how it's a centrifugal pump or a centrifugal fan works. But as you can kind of see, it comes in, spins at 90 degrees, and then it develops pressure within this housing, and it comes out. And as a result of that design there, it is able to generate a lot of pressure to overcome a lot of resistance in the ductwork and get that air down a long duct run, perhaps, if that's where we're taking it. And then also there are plug or plenum fans, which are essentially, it's a centrifugal fan with the housing removed, essentially. And so these you'd find inside of air handlers, essentially, or it could be part of a fan wall. You can kind of see how these could get mounted on top of each other or on the side of each other. Fan walls have developed a lot of popularity recently because they don't take up a lot of space, or I should say a lot of depth within an air handler, so you can reduce the length of an air handler, make it not so big and expensive with a lot of the outside casing of it. Also, a fan wall provides some redundancy in case one or two motors go out. You still have some other means of providing some air in that space, which is probably going to be okay if you're not at the design peak load conditions. Okay, let's talk about filters now. Different kinds of filters. The most common kind are pleated filters. Yeah, this is kind of what you probably have in your house if you have a furnace or an air conditioner in your house. It's pleated to provide more surface area, and in doing so, yeah, it can hold a little bit more dirt that way, but also it reduces the velocity through the filter because this media has kind of an upper end of velocity where it works well, and that's usually around 200 or 250 feet per minute. And within the ductwork, we usually like to design it a little bit faster than that so we can have some economies of not making the ductwork so big that way, and a lot of expensive sheet metal. And so by having this kind of accordion pleat this way, it maximizes the surface area such that the air that goes through every little square inch of filter media, it slows down quite a bit to the point of, yeah, ideally, below 250, around 200 feet per minute or so. Then there's a bag filter, and these are meant to just contain a little bit more of the particulates and not change it out so often. Yeah, they're a little bit more expensive, but they hold more dust and particles and so forth, and you just don't have the maintenance cost to change them out so often. Then there's HEPA filters, which stands for High Efficiency Particulate Air Filter, and these would be common in really high purity type spaces, hospitals, labs. They're usually pretty thick, either 8 inches or 10 inches thick, and these can get to about, golly, 99+% efficient as far as removing the particulates in the air. These pleated filters they're not very efficient, maybe 30% efficient, and these bag filters, somewhere in between, maybe 70 to 80% efficient, something like that. And there's other kinds of filters too, but there's electronic filters, which operate in a way that they charge the particles in the air, and then there's plates that it goes through with an opposite charge, and then those charges, like static electricity, kind of pulls those particles to the plates that way. It's a way of removing the particles out of the air without having so much maintenance of just changing out the expensive media all the time. These you can rinse off and replace easily without a lot of material cost. You might have some labor maintenance costs, but not a lot of material cost to change out all of the filters that way. Okay, let's talk about some coils. There are hydronic coils and then refrigerant coils. So the way a coil works is very similar to the radiator of your car. If you can imagine that, if you've seen that, kind of looks like this, where you have tubes that go within the coils, and within those tubes, in this case, is water or hydronic fluid. And hydronic is the name that we give to HVAC water, either heating hot water or cooling water. We don't say hot water or cold water because those terms are reserved for plumbing. If you went to a pipe fitter and asked them to put up some hot water pipe or cold water pipe, they'd tell you, I'm not a plumber. I put up heating water pipe or chilled water pipe. So hydronic came around after plumbing, and so that's why we changed those terms. So heating hot water or cooling either condenser or chilled water. And so these tubes are pretty big, just like the tubes on the radiator of your car. And then air flows by there and it exchanges heat through the fins that are solidly attached to these tubes that way. So there's heat transfer that takes place. The heat is transferred from inside of these tubes. If this is a heating coil, for example, the water inside of these tubes would be pretty warm, and it would exchange the heat to these tubes, and then those BTUs, those British thermal units, that is the means of moving the heat that way. The air comes by and picks up those BTUs, picks up the heat from the heating coil through these tubes. And so a heat exchanger is basically a device that exchanges heat between two fluids. And a fluid could be air or water. So in this case, it's air and water in this case here. And so that is how a hydronic fin tube radiator coil mechanism works. And then there's a DX coil, which works in a similar way. The air goes through it and it's exchanging heat with refrigerant. And we call that either refrigerant or DX, direct expansion. And you can distinguish the difference between these because the refrigerant coils have these little capillary tubes. They're much smaller than the hydronic coils. We have a much higher pressure within a refrigerant system, and so we can pump that refrigerant through smaller lines, and we just have a lot more tubes, and we just a different way to get heat transfer that way from the refrigerant into the air. Okay, let's talk about dampers. Dampers. What is a damper? No, not a diaper, but a damper. Well, a damper is the air equivalent to a valve. Yeah, I think everybody probably understands what a valve is. A valve is means of controlling water within a piping system. And so a damper is the air equivalent to that. It's the ability to control the amount of air that's flowing through a duct. Let's talk a little bit about different kinds of dampers here. So here's just a manual, pretty small, little cheap damper. This is what you might find right before a diffuser. So off of a trunk line before it goes into a diffuser. And you can turn this little handle and it turns a little blade inside of there, just a little round blade to meter the amount of airflow that flows through it. Here's another manual balancing damper, but this is going to be a little bit more expensive here. And this is just a little more heavy duty. It could be for a larger size duct, so it's not so flimsy. It could be for higher pressure applications, and sometimes there might be gaskets around here if you want it to be really tight sealing. And then with this type of a damper here too, it's important to understand some of the terminology. There are parallel dampers, and then there are opposed blade dampers. So here's a picture of an opposed blade damper where when you turn this, the linkage of the dampers, they will turn opposite. So within a parallel blade damper, they all turn in the same direction. When you turn the shaft, they all open and close in the same direction that way. With an opposed blade damper, they move in, each one moves opposite to each other. And so what's the significance of that? Well, as you can kind of see, within a parallel blade type situation, all the air gets kind of forced against one side. So if this is closed, maybe to like a 45-degree angle here, maybe halfway closed. The air is going to come through here nice and straight, but then it's going to get pushed to one side. And then if you have an elbow or some kind of a fitting, maybe a squirt around or a reducer after this, it's going to introduce some turbulence that way. So an opposed blade type damper, that tends to keep things going nice and straight. It squeezes it through. Yeah, you might have a few eddies around here, I suppose, but they're just different. And so anyway, it's just important to understand the differences there. Then there's control dampers, which is usually the same type of damper as these manual dampers, but instead of a hand-operated type mechanism on the outside that's lockable in one position, there's an actuator on the outside, and that actuator receives a signal. It could be from a thermostat, it could be from a variety of things, and that would control the position of the damper. So if it's going to move frequently, then we would have an actuator on the outside, and then again we'd have some controlled sensor that this would be the device that controls the damper basically. Then there are fire dampers. The way a typical fire damper works is there's a fusible link here which is made out of some kind of material that melts at a certain temperature, between maybe 160 and maybe 200 degrees or so. You can buy a fusible link for different temperatures depending on the application. If it could get pretty warm or something, you don't want it to fail under normal situations. You know, if you're running hot air in here, you might want to have it at a pretty high temperature just to make sure it doesn't give a false actuation that way. But when that fusible link hits its temperature of where it melts, it links and it releases this little accordion type damper, kind of like that pleated filter. That's kind of how it looks like, in this metal little accordion wall basically falls down, and it prevents any flames from going through the ductwork that way. Then there's a fire/smoke damper, which looks kind of similar to a control type damper, and it just operates in a little different way. It's got an actuator on the outside, and it is usually activated by some nearby smoke sensor. If it senses smoke, this just closes off real tight. But it's also rated for fire. So these are usually pretty expensive dampers of everything that we've talked about here so far. These are pretty expensive, just not only are the way that they're built, but also they'll take an electrical connection from the electrician, not just the controls contractor with low voltage wire in this situation, but there's some interface with the fire alarm system and with electrical, and so the whole total installed cost for this fire smoke damper is usually pretty expensive. Okay, and so all of those parts that we've talked about here get put together within an air handler. So now we can kind of see how all of those parts fit together within a system here. And so here we have a couple of fans here, and this is a pretty complex air handler here. So in this situation, we have a fan here that pushes air through what looks like is a heat exchanger, maybe exchanging heat between the outside air and the exhaust air. And so the supply air could come in down here and get filtered, maybe goes through this coil and gets tempered. And then we have another fan here, and it looks like this, to save space, this is kind of a double-decker air handler. Most of them are just kind of a single tunnel, but this is kind of a dual tunnel. It's going to go over here and go up, and then kind of come back through maybe a set of final filters. So maybe this is for some really clean operation, maybe for a hospital or something. And it's going to turn again and go up through here, out this outlet. And notice we have some actuators on these little dampers here to control them for a variety of means here. It could be for economizer. And there's another video that we have in this beginning level series about economizers, so we'll talk more about that in that video, but make sure that you see that if you're not familiar with the concept of an economizer. And then, you know, the dampers that either exhaust the air or bring in the outside air, they have little actuators on there as well. So there's all the components within an air handler system. Let's talk about some wet parts now. of a HVAC system. So mechanical systems, we talked about hydronic fluid going through a coil, and that has to get pumped somehow. And so we use these pumps, we use these hydronic pumps, and they can be either centrifugal pumps or inline pumps. What is the hallmark of a centrifugal pump again? Or a centrifugal anything? Yes, it comes in here and it gets discharged 90 degrees from how it comes in that way. So there's just a propeller in here, basically within this volute, this casing of it here, and it generates a lot of pressure and it discharges the air through the piping in that way, 90 degrees from how it comes in. An inline fan is generally for a little bit smaller pumps, a little bit easier to install, maybe takes up a little bit less room, less fittings and so forth, and so you could put it straight kind of in line, just like the name of it implies, within your piping. Now, it's kind of a misnomer a little bit. The way that it's piped is in line, but the way that it works is still a centrifugal pump. If you can look at this here, you can kind of see the manufacturers designed this to come in and make a hard 90-degree turn inside here, and then it spins around. So really, it's kind of a centrifugal pump, but just cast in a way such that it makes it easy to install in the field in line, where the inlet and the outlet are kind of in the same plane that way. Okay, let's talk about boilers. So there's condensing and non-condensing boilers. And you probably won't see a whole lot of non-condensing boilers anymore, but there's a lot of them out there that are existing, so we'll talk about them a little bit. The difference between condensing and non-condensing boilers basically is how much heat is rejected into the atmosphere from the boiler. So non-condensing boilers are typically only about 80% efficient at the most, maybe a little bit less than that. So that means 20% of what you pay in energy that you burn, the fuel that you burn, if it's either propane or natural gas, goes out the flue out of the roof that way. Well, why don't we take more advantage of that? Why don't we, why can't we get these things to be 95, 96% efficient? Well, we can, and that's what a condensing boiler is for. But when you wring that much heat out of the flue before it escapes the building that way, what tends to happen is it cools down to the point where the products of combustion, they condense inside the flue. They condense on the walls of the flue, and they'll drain back down inside your boiler. And those products of combustion can be pretty aggressive, pretty corrosive. So not only could they rot away your flue, which is not a real big deal because you could replace that fairly inexpensively, but if they get down to your heat exchanger, they could rot away your heat exchanger, and that can be pretty expensive because inside that heat exchanger is a lot of money. That's where, there's either fire tube or water tube boilers where the flames either go through the tubes or the water goes through the tubes and the flames are on the outside. But that's how boilers exchange the heat between the flames and the water, is within tubes. This is called a shell and tube heat exchanger. There's a shell on the outside and there's tubes on the inside, and the water and flames never come in contact with each other. But as you can imagine, the flames, the heat from the flames can give up its heat to the water that way. So a condensing boiler is designed such to extract as much heat as possible before it leaves, and those can go up to maybe 96, 97, 98% efficient, depending on some temperatures of the water, essentially. And these are what condensing boilers would look like. The way that you can tell them apart if you saw them in the field is that usually a non-condensing boiler would have a metallic flue, but sometimes condensing boilers could have a metallic flue too. These would be usually stainless steel, perhaps kind of a shiny stainless steel exterior, but they could be PVC as well, or polypropylene is a real effective, inexpensive flue for condensing boilers. It just depends on the manufacturer, really, whatever their recommendations are for the size of the boiler and the temperature of the flue gas too. So condensing boilers are a lot more energy efficient, but as you can imagine, they're a lot more expensive too. And so that's the trade-off. There's always trade-offs in HVAC that, if you want something more efficient, you're usually going to have to pay more upfront for it. That's just kind of the way the world works. And like I mentioned, these boilers are usually gas, could be propane or natural gas, but they could be electric as well. You could have an electric boiler. And what do you suppose the efficiency of an electric boiler is? Well, electric boilers don't have a flue, so where else is the energy going to go that you put into it? You've got some elements, and surrounded around those elements is the water. So where else is that energy going to go? Yeah, pretty much all of that energy goes into heating the water. So electric boilers are pretty close to 100% efficient. And so you might think, well, gosh, why don't we just make why do we have gas boilers and have all that expensive gas piping and so forth? Why don't we just have electric boilers all the time? Well, because the price of electricity is a lot more than the price of natural gas for the same amount of heat capacity, or essentially what you pay for the amount of BTUs that you're going to pay to get out of that. You're going to pay a lot more with electric, just due to the cost, just the utility bills, than natural gas. Even if you had to let 20% of your bill go up through the flue, it's probably going to, it depends on what area of the country you're in, but it's probably going to be a little bit more efficient to use natural gas or propane even, than electric. And we talked about hydronic pipe, or hydronic, meaning water. You could have steam boilers too. Steam is getting pretty rare. You typically only see it in systems that are used for some process, maybe for hospitals, for autoclaves to clean their devices, maybe for humidifiers in areas of the country where the energy code would allow steam humidification for the air. But they're usually not used for general HVAC heating anymore. Why? Well, because they're kind of dangerous. They operate under a higher pressure, and plus, good steam fitting journeymen that work on these systems are getting harder and harder to find. Those people are kind of rare dinosaurs now. You don't see too many new, younger people getting into the trades and saying that I want to be a steam boiler, a maintenance person and an operator. It's just rare that way, and so usually it's hydronic or for some specialty system that is smaller, low pressure, and so on. Okay, the other way of providing some heating water within a system would be an air to water heat pump. And so this uses a refrigeration cycle, and there's another video that we have in the beginning series as well for how the refrigeration cycle works. So make sure that you watch that if you're not familiar with it. But it uses the refrigeration cycle and electricity basically to pull heat from the ambient air outside, and it pulls that heat in through the efficient means of the refrigeration cycle. It pumps that heat into the hydronic loop, basically into the water essentially. So there's some heat exchangers within here. Here's where this air to water heat pump takes the heat from the air, and it's going to bring that air within a heat exchanger through the refrigeration cycle basically, and it's going to pump out hot water. So that's a pretty efficient way to get heating hot water, as long as the ambient temperatures are in the proper range. If it gets too cold, these don't operate. And that's kind of intuitive, because if the ambient air is pretty cold, well, there's just not a lot of heat to be able to pull from to pump into your system. If it's warmer out, if it's 50, 60, 70 degrees, well, by all means, there's plenty of heat, and this works pretty efficiently that way. But usually you don't need a lot of heat if it's 60 or 70 degrees outside. So that's where the trade-offs need to happen that HVAC engineers think about, is that, well, can we use this for part of the year perhaps, and then What's getting pretty popular now with the phase out of carbon and natural gas is to use perhaps an electric air-to-water heat pump to provide some heating water. But when it gets really, really cold, you would just use a straight electric boiler, because at that point that's going to be more efficient than an air-to-water heat pump, because these are just going to fail to pull the heat if it gets really, really cold, depending on the manufacturer. But if it gets down to 20 degrees, 10 degrees, yeah, it's probably going to make sense to have an electric boiler for backup that way. All right, we talked about heating in a hydronic system. Let's talk about cooling in a hydronic system. And so we do that with these devices called chillers. And you can either have an air-cooled chiller or a water-cooled chiller. Let's talk about how those work. So an air-cooled chiller works about the same way as the air-to-water heat pump did in the previous slide. In fact, it looks very similar. It's got the same components. It basically just works in reverse. And so unlike an air-to-water heat pump where it pulls the heat from the air and it dumps it into our piping system, this is going to do the reverse. We're going to pull the heat from the building with this hydronic system. So we're going to have a pump here, and it's going to pump chilled water. Don't worry about where we get that chilled water for right now, but we're going to have chilled water flowing through these fan coils. Remember the coil that we have? We're going to have these fan coils in different zones within the building, and those are going to absorb heat within the space. And as they absorb the heat, it's going to get, that water is going to get warmer. It's going to get returned here. When it gets returned to the chiller, it's going to go through the refrigeration cycle. Again, make sure that you watch the other video on the refrigeration cycle to more specifics as to how that we move the heat here from the one heat exchanger called the evaporator to the other heat exchanger called the condenser. And then we're going to reject that heat to the ambient air through these coils here. So in the air-to-water heat pump in the previous slide, here's where we're going to pull the heat from, pull it inside the building. But in the case of an air-cooled chiller, we're going to reject that heat through the air through this means. So pretty much the same device, it just works in reverse that way. And then a water-cooled chiller is pretty similar in the way that it produces the chilled water. The difference is how we reject the heat. So instead of rejecting the heat through means of these air coils, we have DX flowing through these coils, or refrigerant, and then we have air flowing through them. Here we have refrigerant flowing inside of this shell and tube heat exchanger, and then on the outside of that we have water. And so water is a much better medium for heat transfer than air. So as you can imagine, this could, we could have a much bigger capacity machine here with a water-cooled chiller than an air-cooled chiller. The capacities of an air-cooled chiller tend to top off at around, economically about 100 or 200 tons perhaps. You could have more. It's just they get really big on your roof or your ground. So much more than that, sometimes it might make sense to have a water-cooled chiller. And these could go up to, 5,000 tons or more. And it's mainly due to the efficient means of heat transfer between water and refrigerant versus air. I think that's fairly intuitive, because if you stood outside in a 90-degree environment, depending on where you live in the world, you could exist in 90 degrees okay. It's warm, you'd sweat a little bit, but it's not, you could stand out there for quite a while, and many people do across the world in hotter temperatures than that. However, if you were to be in a 90-degree hot tub, if you've ever checked the temperature on that, 90 degrees is pretty doggone warm. It's usually not that warm, but you can check it next time you're in a hot tub. But if you're in a 90-degree hot tub, you're probably not going to be able to stay in that for much more than about 10 or 15 minutes before you get sick or ill, sick to your stomach. And that's because water exchanges heat so much better than air that way. All right, so where does this water go then? Once we go through the refrigeration cycle, we've moved the heat of the building from the fan coils through our hydronic water system, and we have exchanged that heat. The heat's finally in this water. Where does that go? Well, that water is going to go to a cooling tower. The that you may have heard of. And so we're going to pump that water from the condenser barrel. Again, if that's unfamiliar, make sure that you watch the video on air conditioning. So that condenser water, the heat from the building essentially, is going to get distributed inside of this cooling tower. And what a cooling tower is, it's a means of spreading out water over a lot of surface area for evaporation. Because what happens in evaporation is you remove heat. Evaporation, in order for evaporation to happen, it has to pull heat. So in order for water to move from a state of liquid to a gas, it must absorb heat. And so we're going to force evaporation by spreading out that water over a large surface area for evaporation to happen. And then there's a fan within a cooling tower. It's usually an axial fan, because why? Axial fans are good for moving a lot of air and through not a lot of resistance, not a lot of static pressure. And there's not a lot of static pressure within these units here, not like a long duct run. You could have a centrifugal fan, but it's usually most common to have an axial fan at the very top of this. And so we're going to force evaporation at a very high rate. We're going to force basically just wind across that water to evaporate it. And so this works very similar to how you keep yourself cool when you sweat. So when you get warm, our bodies have adapted to sweat. We form, get moisture on the outside of our skin, and then we evaporate. That sweat evaporates, and as it evaporates, again, the liquid must have heat in order, or it must absorb heat to change from a liquid to a gas. And so when that sweat evaporates from us, we feel cool. That's how we've adapted to stay cool when it's really hot out. And when you step inside of a cool, dry building that has air conditioning in it, you feel really cold. If you come in, if it's 90 degrees outside, you're all sweaty. If you come into a cool, dry building, you feel really cold all of a sudden. It's because it's colder, number one, but also it's dry, and so that dry environment evaporates the sweat off your skin really fast. And so that's why you feel extra cold when you step into a cool, dry building that way. So same concept with the cooling tower, is we're going to force the evaporation of that water at a really high rate. And when we do so, that's we kind of think of that as free heat transfer, or we're using the natural thermodynamics of evaporation to remove heat. And so it's a real efficient way to remove the heat from a building through natural evaporation that way. What are the downsides of a cooling tower? Well, several. It's a lot of components. In the previous slide, the air-cooled chiller, everything is packaged basically in one device, and that's all you have. Here you're going to have some water treatment within your piping to prevent algae and corrosion and so forth. But also you just have more parts and pieces. You have a separate whole condenser water system, and but the energy savings on this is a lot better than an air-cooled system. And so if it's something that you're going to have, if it's a large capacity building, a lot of tonnage, then it would probably pay off if you're going to have it for a long period of time. Those are some of the things that an HVAC engineer thinks about when they consider the system and talk to the owner as to how they're going to use it, if they're going to operate it for a long time, if they're going to maintain it themselves, and so forth. One other consideration with cooling towers versus an air-cooled chiller is that the air coming off of this cooling tower is very warm and moist, as you can imagine. It's absorbed, it's steam basically. And so in the wintertime, when these are working, you may have driven around some industrial areas and seen some fog coming off some equipment. That's usually a cooling tower, and when it comes off of here after a few feet, that warm, moist air condenses in the cool ambient air if it's in the wintertime, and it forms a cloud. And it's basically the same way that clouds form naturally in the air up in the upper atmosphere, is that it becomes so moist and the air temperature is so cold that the air cannot stay in suspension anymore, and it condenses out in the form of a cloud. And you can Google or YouTube a little bit more on the meteorology of how clouds are formed if you want. But from an HVAC design standpoint, something you should be aware of is that's one of the big differences between a cooling tower and a air-cooled chiller, is that the discharge of these can produce a fog plume. And so a realistic consideration for that is perhaps a hotel. You know, if you got a 10 or 12 story hotel or something, and if you put this cooling tower down on the ground, well, there's certainly the potential in the wintertime, if that operates, which it may, because there might be a lot of interior loads within the hotel that they need cooling year-round. And so to get rid of that heat, we get rid of it through a cooling tower, and it could condense in the wintertime, and that fog plume, you know, it could blow up against guests' windows and maybe even, you know, kind of fog up the exterior of those windows, perhaps, even if it's not raining. And it could create kind of a undesirable experience for the guests. So just something to think about. So could you put that on the roof to mitigate that? Probably. Or someplace where it's not going to be seen? Yeah, you could probably do that. There's ways around that. So just considerations about that. Okay, and then finally, we talked about in the list here, there's open and closed different types of cooling towers. We talked about how they work and considerations. So an open cooling tower is an example just right here where the water that comes from your water-cooled chiller directly spreads throughout the fill material, and that water is exposed to the atmosphere. It's open to the atmosphere. And so what that means is that water that falls to the sump here and gets collected within this big sump and returns back to the chiller into the pump, that could contain a lot of contaminants in there. Oh, it could be leaves, it could be cigarette butts, it could be dust, who knows. Now there's filters within here it's called a strainer. It's like we can strain out most of that stuff, but it's a maintenance thing. You know, we gotta clean out that strainer every so often because it's going to have, you know, a lot of just things from the atmosphere floating or getting into that sump. Not only that, but as this water evaporates, what happens when water evaporates? What do you typically see on your shower after years and years of operation if you don't wipe it down after every use? It tends to build up those hard water deposits, right? Kind of that cloudy scale that's really, really hard to remove. And that's the same thing within this piping system and within the heat exchanger of your chiller. So as the water evaporates and the water becomes more and more hard, the hard water deposits that are left, usually from calcium, is what the hardness comes from. That precipitates out in the water where it is the warmest. And where in the system is it the most warm? Well, it's going to be in your chiller in that condenser barrel. And so that's going to collect a lot of these hard water deposits. And what are the implications of that? Well, as that scale tends to build up, it builds up this layer of insulation, essentially is how it operates, within your heat exchanger. And the more that scale builds up, it prevents good heat transfer. For heat transfer, we want nice, clean surfaces of metal between both fluids. If you build up a lot of scale, you know, you can imagine if you build up a 1/16 of an inch or an 1/8 of an inch would be a whole lot. You'd never get that much, but even a 1/16 of an inch could dramatically increase your energy bills because it's just going to make your equipment work harder to get the same amount of heat transfer that it did when it was nice and clean. So to prevent that from happening, we have these closed cooling towers, or sometimes we call them a fluid cooler or a closed cell cooling tower. And the way this works, the actual cooling of liquid happens the same way. We have an axial fan up on the top here, and we have some fill material which maximizes the surface area of the water that we use to evaporate to get the heat out of. But the water that goes to your chiller, however, goes through a coil. There's a big coil that goes back and forth here, kind of like the water coil that we saw, you know, like an air coil. So we have your hydronic fluid in here, And then on the outside is another fluid. That's going to be our outside loop of water. And here's that little pump that just pumps water from the sump down here, and it goes back up to this distribution manifold that spreads the water throughout all the fill material. So we have this water, which is kind of cool, and it sprays over top this big coil. You can kind of see it's offset here because it kind of wraps around a few times and comes back out here. So it's not quite as efficient because anytime you have a heat exchanger, you're not going to have 100% efficiency of heat transferring from one fluid to the next. It just doesn't work that way. You have a little bit of inefficiency within the metal. And this is not going to be as efficient as an open cooling tower. However, it does prevent some maintenance, and it keeps your heat exchanger surfaces of other equipment, like your coils and your chiller condenser barrels, nice and free from scale, and at least those are going to be a little bit more efficient that way. All right, I think we about killed cooling towers there. So where does that chilled water go? Back to the chiller. So we make chilled water through the efficient use of the refrigeration cycle, and then that chilled water is going to be used. We have a pump. We're going to pump that water to these fan coil units. And a fan coil unit, unlike an air handling unit like you saw before, it's kind of a real dumbed down version of an air handling unit. A fan coil unit consists of a fan, as you can kind of see back here, and a coil. And that's about it. And usually a filter. It might be a filter. If it's a ducted fan coil, it'd probably be behind here somewhere. But it could be, if you go into a hotel room, if you look up above in the doorway, as soon as you walk in, there might be a big return air filter grill at the bottom of these. So there's usually a filter and a fan and a coil. It's not usually, there's always a fan, a filter, and a coil, and usually some housing that puts it all together. And that's what makes up a fan coil unit. You could have a 2-pipe fan coil, or you could have a 4-pipe fan coil. What are the differences, and what are the 2 pipes and what are the 4 pipes? Well, 2 pipes is supply and return, as you might have guessed. And so here's where we're going to supply either heating hot water at a high temperature, and we're going to give up the heat, and it's going to come back at a cooler temperature, or chilled water, going to provide it at a pretty cold temperature. It's going to absorb heat, and it's going to come back at a higher temperature. So supply and return of either heating or cooling. And as you're probably imagining right now, if you didn't guess already, the 4 pipes is where you'd have both a heating coil and a cooling coil. And so with the 4-pipe fan coil, you can provide heating or cooling year-round to a particular space. With a 2-pipe fan coil, you can only do one of them. And so this could be maybe a means of cost savings because, well, as you can imagine, this is going to have half the pipe in a system as this would. And piping is a lot to coordinate, it's a lot to insulate, it's a lot of money there to fit above the ceiling and coordinate with all the other trades and so forth. And so I'm not saying if it's good or bad, but it's definitely a money saving idea to have a 2-pipe fan coil. And maybe you have a seasonal changeover, meaning that sometime depending on where you live, maybe October, it's going to get colder to the point where, okay, the plant engineer comes and it's going to turn off the chiller and turn on the boilers, and so now everybody gets hot water or heating hot water within their fan coil units. And if somebody still needs cooling, well, they're just going to be a little bit upset. And then sometime in, I don't know, March, April is when they do the reverse, and they turn off the boiler and they turn on the chilled water system to provide cooling. And if somebody still wants heating, well, they're just not going to get it. However, on the heating side, for when it gets warmer in the spring, though, you could get a fan coil unit with electric heat in there. And that's kind of a compromise, I suppose. You're saving a bunch of the heating water piping, but you just have an electric coil in there. Yeah, it's probably not quite as energy efficient as, you know, a gas boiler and all that, but it's going to be a little bit less expensive up front to have that. So you could essentially have the equivalent of a 4-pipe fan coil in the springtime, and of course the rest of the year it's just that shoulder season, essentially, when you're switching from the chilled water system into the boiler system, there might be some times where some people in some zones would still like to have some cooling still, but once you shut that off, there's no such thing as an electric cooling coil. There is for electricity to heat it, just like a toaster coil, but it doesn't work the same way for cooling. You need to have a refrigeration cycle. And so that gets pretty expensive. Usually, again, if you just wanted to have that luxury, like if you had a hotel, it would, a two-pipe system in a hotel would probably be unacceptable because some tenants just want it warm all the time, some of them want it cold all the time. So if you have that, and a four-pipe system is actually fairly common within hotels because you can think of why that might be. I haven't really gotten into systems yet. We will have some system videos that you can look at that gets into the pros and cons of different types of systems. But for a hotel, a four-pipe fan coil is very quiet. You don't hear any compressors of different systems. And so at the high-end hotels anyway would have a four-pipe fan coil system. And so that gives you the means of providing heat or cooling, whatever the thermostat calls for, year-round. All right, we've talked about fan coils adequately here. And let's just talk about one more part of a system here. A popular system would be, you may have heard what's called a variable air volume system. And so a variable air volume system has a big air handler that, of the slides that we saw, 10 slides or so, that big air handler, and that would deliver air out to these what's called variable air volume boxes. And the way that these work is there's a thermostat down in the room. That thermostat controls this little damper actuator. And here's kind of a cutaway section. There's the damper there. And whatever the temperature of the air that's coming in to that VAV box is, the thermostat can kind of control that damper such that the space is comfortable all the time. For example, if the temperature of the, so it's the same temperature of air being delivered by the air handler to all of the zones within the building. Each zone might have a variable air volume box. And so the thermostat within that room, let's say people start coming into that room now, you've got more and more bodies giving off heat. Maybe they've got computers with them, the lights are on, they're talking, they have some activity, they have some coffee. A lot of heat, a lot of BTUs, British thermal units, being given off within that room. And as the rate of heat is given off more in that room, what happens to the temperature in that room? Maybe the sunlight is coming in too, you got some exterior loads coming into the building. We have another video on loads and zones. Make sure you watch that for sources of heating loads. But yeah, as the heat input is increased within a particular room, the temperature is going to go up in that room. So the thermostat senses that temperature and it says, hey, do something, system. And it doesn't necessarily know what it's connected to, but this actuator receives that signal and says, I know what to do. I'm going to open up this damper to provide more cold air into the space to offset the fact that there's more BTUs in that space that's creating a hot environment. And so it does that. And it finds its equilibrium and keeps the temperature cool within that space. Well, what happens now when the people start to leave? Maybe the lights are off, maybe the sun starts to go down. There's not as much of a load within that space, providing so much heat buildup in that room. It's cooling off. So the thermostat says, okay, do something. I don't need as much cooling anymore. So this actuator says, I know what to do. I'm going to close down. The damper is going to close. So it's going to close to some point. It doesn't close completely. It just closes to some point because we still want to have a little bit of fresh air to come through the system just to keep it from getting stuffy and to prevent carbon dioxide buildup, what we breathe out, because within a space, as you exhale, if you get a lot of carbon dioxide buildup, you get kind of tired within that space. And so we need to have a little bit of fresh air in there. Code usually requires little bit of fresh air within the space anyway. And so, but sometimes the amount of air that's coming in there at the temperature of that air handler is such that it would still overcool the space. You know, if there's maybe only one person within that space, maybe it's at nighttime now, and there's just not a lot of cooling load anymore. You just don't need that much to cool the space. And so to prevent that space from getting too cold, the thermostat is going to register that's getting colder and colder. It's going to tell this VAV box, hey, do something. It's going to say, oh, my damper's out of position. It's at a minimum position. I can't close it anymore. Well, it would, the VAV box would turn on a heater. And so in this particular case, here's the air coming from that air handler, and there'd be a little heater on the exterior of it. And you can kind of see that. It looks like a toaster coil. So that's just an electric coil, basically, an electric duct coil. So it heats up, and these little elements in here get red hot, kind of like the color of the laser pointer there. And we exchange heat between the air and that little toaster coil heat exchanger there, and that's how we reheat the air back up. So anyway, those are kind of the parts of a VAV box. There's some terminology. There is what's called a pinch or a squeeze VAV box. Still variable air volume. The air passes right through here, and we control the volume with this little actuator controlled by the thermostat. And then there's a fan-powered box. The fan part comes from the ability to pull air from the plenum. So if this were installed above a lay-in acoustical tile ceiling, there is some extra heat within that plenum space given off from the lights, from the ballast of the lights. But also in office buildings, it's fairly common to have a plenum, a return air plenum within the space. So it's a little bit warmer in that plenum than below the ceiling. And so this fan can pull in air from that space and use that for the first stage of heat, maybe help to blow that back down. And then if it's still not warm enough to satisfy the thermostat, that's when that heater comes on. This fan also provides means of providing the same amount of air that gets delivered to the diffuser all the time, so that you don't hear a variable amount of air coming out of your diffuser. As you can imagine, if the air volume changed, that might be a little bit distracting. This at times could be quieter than a fan-powered VAV box, but at least this is constant. You don't notice it changing. So those are just considerations. You know, we talked about giving you considerations between different parts of the mechanical system. So those are some things to think about. We'll talk about this more when we talk about different systems of HVAC. All right, and then finally, let's talk about GRDs. You'll hear the terminology GRDs, or grills, registers, and diffusers. And this is what finally distributes the air within a space. It's what gets connected to the supply air or return air or exhaust air of ductwork. And it's what looks a little bit nicer, so that we don't just terminate ducts within a space within just with a plain old duct. As you can imagine, if we had just a duct pointing down from the ceiling, if you walked underneath that, you know, it'd be very distracting. Your hair would get blown around. You'd have this incredible velocity of air directly below that. So instead of that, we would put a supply diffuser in that, and a diffuser helps to spread the air around. So think of how a diffuser works kind of like the opposite of a nozzle. I think we all understand how a nozzle works. Think of a fireman's hose at the end of that. That's a nozzle where it takes, you know, in this case of a fireman's nozzle, it takes water, takes liquid through a hose at whatever diameter the hose is, and it pushes it down to a very small opening. And so for that same volume to go through that smaller opening, it has to increase in velocity a whole lot. And that increase in velocity is what creates, you know, a stream of water on the other side that way. So a diffuser is just the opposite. It takes that stream of air and it opens it up. So as you can imagine, it opens it up here. It does the opposite of a nozzle, and so it slows down the air. So we want to spread the air out and slow it down so that it doesn't create any harsh drafts on the backs of their necks. You know, that would be kind of uncomfortable. So that's how a diffuser works. A register is typically like a sidewall type of a device that you can manually adjust the vanes on. or it could be fixed perhaps. And then a grill is usually something that's fixed, that is usually meant for return air. Lots of different types of grills, registers, and diffusers based on, do we want to spread the air out? Do we want it to shoot a long ways? Do we want it to look nice? So lots of different grills, registers, and diffusers. That way you could Google them to see different kinds, and I'm sure you've seen different kinds within different buildings. There's floor diffusers, there's wall diffusers, there's ceiling diffusers and such. There's diffusers that are mounted on the sidewall of exposed ductwork too. And that completes this video on very introductory high level of system parts. There's a lot more to it than this. If this is something that you'd like to incorporate at a larger scale in your organization with more one-on-one attention and maybe have a Q&A session, please reach out to us at MEP-Precon.com and we can discuss virtual or in-person training on this and a variety of other subjects. And make sure to go to the website to look at the assessment here. Make sure that you score 100% on that assessment. And if you don't, then go back through the video to that part and make sure that you understand it. Or other parts as well, I should say other videos. There's other means of getting this training. There's other videos out there. There's other Googling. The assessment, though, I think is pretty unique. If you're not going to take some kind of assessment after a video, it's just essentially entertainment, or at best edutainment. So really make sure that you test your how much you've retained, and taking that assessment will help to make sure that you retain it longer that way too. So make sure to check back here often at MEP-Precon.com for us to add some more videos, and look forward to seeing you on the next one. Thank you.